Now I'm going to drop a pine cone from a tree, and I want to know how fast it's going when it hits the ground. Previously, what we've done is we've written out our equations. I've gone like delta y equals v naught t plus 1/2 at squared. Once the other one I have is v final squared equals v initial squared plus 2a delta x. And then we do some work and kind of figure out how we could solve this given just this, right? So with energy, I ask myself, what energy does it have in the beginning? And in the beginning, I look at this, and the only thing it has is this potential energy relative to height. So there's its potential energy. It says that if it falls down, it's going to convert this potential energy into, at the bottom here, it will have kinetic. So I start off with all potential, I fall, I speed up until I hit the ground, and now I have all kinetic. This is the split second before it hits the ground, before it loses any of that energy. It's all conserved. So from here, then, I can look at that and be like, okay, so what do I have? When I look at conservation-wise, I have potential energy going into kinetic. There's no wind. It's not losing anything. Cool. So I'm going to rewrite that as mgh equals 1/2 mv squared. And I look at that, I'm like, oh, it's mass cancels. Nice. Move the 2 to the other side, and I get 2gh equals v squared. Nice. I kind of feel like this looks a little familiar, though. I kind of feel like, let's see, this one, I'm starting off at rest. And let's see, A is G. And our delta x here is our delta y. So delta x, that just equals h. So that means that I have then v final squared equals 2gh. Oh, look at that. It's almost like one came from the other. There's a relationship there. Okay. So now we can put things in. But I get velocity then equals the square root of 2 times 9.8 times 5. Sweet. I can crunch that out. Actually, let's go ahead and do that real quick. Because I'm going to follow up with a question that we can add to that. 9.8 times 5 to the 1/2. Gives me 9.9 meters per second. So let me ask you this. And I want you to pause and come back to it, and I will work it through. What if V final equal, instead of that, equal like 5 meters per second? Wouldn't that mean that I had some non-conservative force, something taking energy out? So pause this. How can I rewrite that? And we'll call that wind. There's wind blowing. It's going to fall down into the wind. That almost looks like wind. Pause. How are you going to do that? All right, let's see. So what do I have? I have potential energy. What can we think in terms of this wind? I have work. I kind of look at this, and I'm like, okay, I have potential energy. If I have nothing taking energy out, all of it goes into kinetic energy. So another way to think of that is that I'm going to lose work from the wind. What I have left after is what's making it go. So in this case, the question I asked is, what is the work from the wind? How much energy has been taken out? So you have a couple of options here. What you could do is take this thing and then turn it into energy and subtract that from mgh, which is essentially what we're going to do here. I'm going to go then potential energy minus the kinetic energy will give me the non-conservative energy that work was. That's the energy work took out. So then again, I have mgh minus my 1/2 mv squared equals the work from the wind. I'm writing it out like this because up till now we're like constantly canceling masses out. I have this unknown work from the wind. Doesn't have a mass. Can't cancel these. So I need to put these in completely as their values. So now I would just put in my numbers, and I'm not going to crunch it out, but I'll just put the numbers in so you see it. Did I say, oh, let's call this 1 kilograms? Because I'm nice that way. So we have 1 kilogram times 9.8 times 5 minus 1/2 times 5 squared will give me the work from the wind. And there you have it. So we could take one scenario and turn it into a whole nother one and learn how to work with that. Work.